Jason joined us in 2008. Before that, he was at Lynchburg College, where he became the first member of his family to get university education. He worked for a while, decided that BS was not enough, and 6 years later, here we are. Jason worked one summer in Microsoft Research, and the rest of the time he spent at Cisco, so his Cisco family is well represented here. And what makes this event particularly special is the presence of his mother, sister-in-law, and wife in the audience. And in fact, his wife Unique is the reason why we're having this defense before school closes for the summer, because they expect a child later in the summer. So such deadlines are just wonderful. Jason's work is on software development. So of course, Fred and David Stotts are on this committee. His work involves data mining, and that's why Wei Wang is on the phone. In fact, his first research result was in Wei Wang's class when she was a faculty member here. And his evaluation involves human subjects, and that expertise is provided by Diane Kelly here. So it does take a village. He's going to give a talk for about an hour. During that period, we can ask clarification questions. After that, the general audience will get a chance to ask in-depth questions. Then committee members will ask public questions. And at the end, there'll be a private session with these committee members while the rest of you enjoy the healthy refreshments outside. Okay? And we do have a deadline. Diane and Wei both have to be done in 2 hours. And so we will be done by 5 o'clock. Okay, Jason?
Okay. Thanks for the introduction, Prasoon. Good afternoon, everyone. This talk is about collaborative software development. In such development, developers work together for a variety of reasons, such as clarification of tasks, to divide tasks, and to resolve conflicts. A relatively unexplored interaction is when they provide help. When this happens, they are prevented from making their own progress. Which brings us to my first research question. What happens to the overall productivity of a team when developers provide help? Three research results may provide an answer to this question. The first result by Herzog et al. Showed the co-located teams, that is, teams that are in the same building but sit in different cubicles, are more productive than distributed teams, that is, teams that were geographically dispersed locations. The second result showed the radically co-located teams, that is, teams that sit in the same building but in a single war room or bullpen, were more productive than co-located teams. A major reason was, if someone was having difficulty, another developer walking by, seeing the activity over their shoulders, would stop and provide help. The third study showed that pair programming teams were more productive than solo programmers when taking into account the cost of fixing bugs. Together, these studies suggest that the productivity of developers increases when they help each other, and as distance increases, help is offered less. So how do we make help independent of distance? We can either reduce the need to ask for help, or we can promote help. My work was on help promotion. And there are two ways to promote help, either social or technical approaches. And my work was in technical approaches. And we can develop tools that allow developers to either actively ask for help or observers to passively notice the need for help. And my focus was on passively noticing the need for help. And the reason is the three productivity and distance studies I've mentioned earlier motivate passive help awareness. This brings us to my next research question, which is, how can we make passively noticing the need for help independent of distance? We can do this by virtually simulating face-to-face software development, and there are two cases: pair programming and radical co-location. First, let's look at pair programming. To virtually simulate pair programming, a helper will watch two screens, one of the developer and one of the developer screens, and they can use this information to determine when to offer help. A limitation of this approach is it doesn't scale, because developers can be aware of at most only a few developer screens. So a more scalable approach is to use video walls, and these are walls that show the activities of remote teammates in one room. However, teammates may still miss the opportunity to help each other. A fundamental problem of both of these approaches is that they are being their approaches, and this means they try to simulate face-to-face interaction. One way to address this limitation is to go beyond being there. That means providing capabilities that are not available when developers are face-to-face. So in my case, this means creating a mechanism that detects when developers are having difficulty and communicates this difficulty to some teammates. It is my thesis that automatic difficulty detection is possible and useful. I've developed two tools, a difficulty detection tool and a help awareness tool. And I will demonstrate both tools using a video, and then we can discuss research concepts. So this video is going to show a participant in one of my studies actually using the difficulty detection tool while they are trying to complete a task. There we go. And so while they're programming, we're going to see in the corner that the tool predicts that they're making slow progress. So when someone is having difficulty, what might they do? They may go to Stack Overflow, and if that does not work, then they may ask for help. And in that case, that's me. So as we can see here, they're actually typing into a WebEx chat window to ask me a question. And they're trying to figure out how to draw a rectangle using the AWT SWT toolkit. And so help is provided in the form of a URL, as we see here. They click this URL, copy and paste this code into their programming environment. And then they must integrate the code with their old code. So I've demonstrated these two tools with a video. Now let's discuss research concepts, which brings me to my next research question. How should difficulty be inferred? Well, before I can answer this question, I must define what I mean by having difficulty. Having difficulty is developers' or observers' perceptions that developers are making slower than normal progress. And I use both of these perceptions as ground truth. So the argument for using developers is that they're programming, so they should be in the best position to know whether they're having difficulty. Additionally, observers are not mind readers. However, previous work has shown that people tend to underestimate their problems. This means the developers may not always admit that they're having difficulty. In field studies, I use developers as ground truth because there are no screen recordings for observers to view. In some lab studies, I use both developers and observers because there are screen recordings. And in some lab studies, I only use observers because developers did not indicate their status. So how do we capture these perceptions? Let's start with developers. So I'm not the first person to face this problem. In fact, Fogarty et al. Faced it. We're trying to develop a system that uses developers' interactions with the programming environment to determine their interruptibility. Their approach was to randomly interrupt developers and take the time it took for them to respond to an interruption as their interruptibility. I cannot use this approach because it's likely that no random interruption would find that a developer is having difficulty. In fact, having difficulty is a rare event, and this chart is from one of my experiments, and developers only indicated that they were stuck 3% of the time. So a better alternative, one taken by Kapoor et al., was to allow participants to use buttons to indicate their status. And they allow participants to indicate their frustration level by clicking on I'm frustrated or I need help buttons. However, developers still may forget to indicate their status. So an alternative approach, the one I took, is to develop a naive algorithm that actively guesses the progress status and allows developers to correct these predictions. The hope was that developers may press buttons if they're notified. However, this is not fully reliable, which is why I use observers. I built a video observation tool that allows observers to view portions of screen recordings, and then they can mark these portions as making progress or having difficulty. So now that I've defined what I mean by difficulty, we're now ready to answer the previous question, which was, how should difficulty be inferred? This was a long process, and I've taken an iterative approach, which I'll discuss in detail as we go through the talk. But first, I started with developing an initial algorithm for predicting the stuck status and allowing developers to correct this algorithm. But the question is, what should this algorithm actually be? Well, no previous work has addressed difficulty, but there has been some work in frustration detection. So I thought maybe I can borrow techniques from related work. And as I mentioned before, Kapoor et al. Infer when children playing a Tower of Hanoi game were stuck using plasticine chairs, wireless Bluetooth skin conductance test, pressure mice, and a video camera. They input this information into a frustration detection module that predicts whether the kids were frustrated or not frustrated. But a practical problem with their approach was the overhead of using the non-standard equipment. This approach is overcome to some extent by Stiano et al., who used webcams to detect when participants were frustrated or not frustrated. More specifically, they input facial expressions into a frustration and confusion module that predicted whether they were frustrated or confused. This approach has two practical limitations. The first is using non-standard equipment for programming tasks, and the second is that webcams may invade developers' privacy. These approaches have an additional limitation, which is difficulty and frustration are not the same emotion. So to summarize, using non-standard equipment for programming tasks has three limitations. Privacy, overhead, and frustration and difficulty are not the same emotion. One solution to overcome this problem is to use standard equipment for programming tasks, and in my case, programming environments. And the idea was that developers regularly use some form of a programming environment, whether that's editors or debuggers. And since we're using a programming environment, we can log developers' interactions with it to determine whether they're having difficulty. And the insight here was that when developers are having difficulty, the nature of interactions with their programming environment may change. So this is a solution that I took. I input developers' actions into a difficulty detection module that predicted whether they were having difficulty or making progress. The basic intuition is to monitor developers' progress, and when their progress is less than some threshold, indicate that they're having difficulty. To get an idea of how to measure progress, I looked at productivity because there's been a lot of work in measuring productivity, and I thought they were related. However, progress and productivity are fundamentally different. Productivity is measured after developers have written code, where progress is measured while developers write code. So the question is, at what point should I make my emphasis? At this point, that point, or any of these points? I make emphasis after some segment of work. These segments have several dimensions. They can be the size, they can either be fixed or dynamic. These dynamic or fixed segments could be split by the number of commands or the amount of time, and they can be overlapping or non-overlapping. I used fixed segments that were split by the fixed non-overlapping segments that were split by the number of commands. So I've talked about segments. What size should they be? Well, if they're too small, there's not enough information to determine a pattern, and predictions may be made early. And if they're too large, multiple patterns may occur, and predictions can be made late. To illustrate, consider this log. If we only use one segment, If we only use one event, that's not information to determine whether participants are stuck. And if we use the whole log, we're predicting productivity instead of progress. I experimented with several different segment sizes, and I found the size of 50 to work best. Now that we know the segment size, we can go back to trying to figure out how to measure progress. And there's been little work on measuring progress. The only work I could find was done by Kirsten and Murphy. They developed a tool called Mylar, which shows developers items related to their test. They measured the success of that tool by determining how the tool changes developers' edit ratio. The edit ratio is the number of edit commands divided by the number of navigation commands. I use the edit ratio as input into a naive algorithm to predict when developers were having difficulty. I put this algorithm into an Eclipse plugin, and I allowed 3 freshman students that were doing class assignments, and 3 graduate students that were doing class and research assignments to use the algorithm and correct incorrect predictions. So my results show that the naive algorithm did not predict status very well. So this forced me to step back, and I decided to analyze the logs. And what I found was sometimes developers do not navigate. So I had to step back and do some top-down thinking and bottom-up analysis on what behaviors indicate difficulty, which meant I needed to create new ratios or a new set of features. Features are what indicate difficulty. I found 5 features. The edit ratio is the number of edit commands divided by x, where x is the sum of all commands. The debug ratio is the number of debug commands divided by the x, which is the sum of all commands. And the focus, navigation, and remove ratio follow a similar pattern. To validate these ratios and show how indicative they were of programmers' behavior, I graphed them. And here I show 2 graphs, a graph of participant 1 and a graph of participant 2. The x-axis shows the time the programmer spent writing software, and the y-axis shows the percentage for each feature. So for participant 1, when they indicated they were having difficulty, the navigation ratio increased. And for participant 2, when they indicated they were having difficulty, their debug and focus ratios increased. However, in both graphs, the the ratios increased and the edit ratio decreased. So these graphs validate my feature choice. And the next step was to input these features into existing machine learning algorithms. I tried several algorithms, such as the decision tree and the naive Bayes algorithm. But neither of these algorithms perform well on their own. The reason was the class imbalance problem. And by class, I mean a semantic label, such as making progress and having difficulty. And a class imbalance occurs when almost all of the labels are one class and far fewer labels are the other class. This causes traditional machine learning algorithms, such as the decision tree and the naive Bayes algorithm, to be biased towards making progress and to rarely recognize having difficulty. So there are several standard approaches to overcome this problem, and I used the SMOTE algorithm by Chawla et al. And my results showed that the decision tree plus SMOTE performed better than the naive Bayes algorithm. So these are intermediate results, and I will discuss them a bit more in detail. But the point here is that my first iteration was promising, which made me decide to perform a second iteration, where I made 2 key changes. The first was that I aggregated the status of segments. I did this because I found status doesn't change instantaneously. So I used a label aggregation technique that computes developer status every segment and notifies developers every M segments for the dominant status over that range. And I tried different segments, and I found that a M equal to 5 worked best. The second change was to recruit industry developers to use my system. In my previous iteration, I only used students, and I wanted to find out would my approach actually work in the industry. So when I did that, I found developers did not want to use untested tool in their job, and their managers didn't want to use them. You didn't want the developers to use the tool as well. This meant I had to do a lab study. I recruited 14 developers. 9 of them were students, and 5 of them were industry developers. And since having difficulty is rare, I had to ensure that developers faced difficulty during the study, but that tests were not impossible to solve. This meant I needed tests with a known level of difficulty. So I decided to use ACM programming problems from the Mid-Atlantic ACM programming contest. And the difficulty level is determined by the number of teams that solved the problem divided by the total number of teams. So as we can see here, a simple question of chemistry is the easiest problem because all teams solved it. Participants attempted to solve tasks while my tool predicted their status, and I also recorded their screens and allowed observers to indicate developers' status. My results are in the form of a confusion matrix where columns are what my tool predicted and rows are ground truth. And here, ground truth is based on developers. So my results show that developers never corrected a having difficulty status, which means there are no false positives. And false positives means when developers were actually making progress, the tool never predicted that they were having difficulty. However, 24% of the time, the tool predicted progress when developers were having difficulty. So what about observers? Similar to developers, the tool did not give any false positives, but 37% of the time, the tool predicted that developers were making progress when they were actually having difficulty. So how good are these results? Well, no previous work has done difficulty detection, so I had no work to compare my work to. So I developed 3 types of baselines: a randomized baseline that predicts progress 50% of the time and difficulty 50% of the time, a modal baseline, which always predicts the most common status, which is progress, and an actual data distribution baseline, which makes predictions based on the distribution of labels. So I've talked about false negatives and false positives. I could have actually used true positives and true negatives, because you can derive a false positive from a true negative from a false positive, and the same with true positives. So I'm going to use true positives to compare my results to the baseline. So my approach identifies more times when developers were having difficulty and making progress than the randomized baseline. It identifies more times when developers were having difficulty than the modal baseline. And it identifies more times when developers were having difficulty and slightly more times when they were making progress than the data distribution baseline. And the results that are in the red box were statistically significant. And observers, they followed the same pattern. My approach identified the more times when developers were having difficulty in making progress than the randomized baseline. It identified more times when developers were having difficulty than the modal baseline. And it identified more times when developers were having difficulty and slightly more times when they were making progress than the data distribution baseline. And these results were statistically significant. So how do these results apply to real scenarios? Well, no false positives or low false positive rate means potential helpers will not have to stop their work and interrupt developers. While a high false negative rate means developers may spend more time stuck on a problem than necessary. However, we can live with false negatives because missing some having difficulty statuses is no worse than the current practice. And if it is desirable to automatically let others know about the developer's difficulties, it is better to use my tool than to not use it. These results provide evidence to support my difficulty detection subthesis, which is, it is possible to develop an approach that uses developers' interactions with their programming environment to determine whether developers are having difficulty with their tasks and performs better than baseline measures. Encouraged by these results, I wondered, could I perform even better with a third iteration? This meant I could either improve the interaction approach, combine the interaction approach with a different approach, or do both. I decided to combine the interaction approach with a different approach. So now the question is, what different approach? As I previously said, previous work has used many types of non-standard equipment. Kapoor et al. Showed that posture captured by posture seeing chairs was the most predictive. So based on this result, I decided to use non-standard equipment that captures developers' postures. There are many types of postures. So what types of postures should I capture? Well, previous work has showed that body lean correlated with students' affective states such as boredom or delight. More specifically, when students were confused or frustrated, they leaned forward, and when they were bored, they leaned backwards. My hope was that body lean would correlate with participants who are having difficulty. Based on this result, I created 3 categories of body lean: leaning forward, leaning backward, and normal, where normal means neither leaning forward or leaning backwards. Another question is, what type of equipment should we use to capture body lean? Well, the first requirement is that it should be accessible, meaning I should be able to have access to it. The second requirement is that it should be novel, so that I can make a contribution. The third is that it should be widely available, and if it is widely available, my work can apply to a greater number of domains. The Microsoft Kinect camera meets all 3 of these requirements, and it was made available to me by Dr. Henry Freaks in this department. The Intel Gesture camera was also made available to me by a visiting scholar who worked with Persoon. However, it only meets 2 of these requirements because it's not widely available. So I will discuss the Kinect camera because it gives better results, but the results of the Intel camera are discussed in the thesis. So this brings us to my next research question, which is, how should body lean be captured using the Kinect? To answer this question, I performed another user study where I recruited 10 participants, and as we can see here, the Kinect camera is placed above them on a stand. This camera captures the X, Y, and Z coordinates of 20 joints at 30 frames per second. But the problem was the Kinect could not capture all joints. The reason is because the desk the developer sat at occluded their lower body. So at this point, I decided to try to put the Kinect in different positions, and nothing seemed to work well. And around this time, Microsoft updated their Kinect software. They made a seated mode, which is designed to track users who sit and does not attempt to capture joints below the hip. Another problem was that sometimes the Kinect did not recognize the arm and shoulder joints, and that can be seen in this image here. So the green lines are arms the Kinect recognizes, and we see that the arms are by the participant's side. But if you see his actual arms, one arm is on his chin and the other arm is on the mouse. But the Kinect did recognize the head joint the majority of the time. So I decided to use the head joint, which is the distance from the head to the Kinect camera, to measure body lean. And this was the Z coordinate of the head joint in meters. So how do I convert this head distance to body lean? I clicked and messed up. Okay. So this video demonstrates a participant who's leaning forward right now. Then he's in a normal position. And he leans back and then leans forward. Fidgeting makes it difficult to correlate body lean with difficulty. To address this issue, I averaged the head distance per minute, which is very similar to the label aggregation technique, and I input this information into the K-means algorithm, and this seemed to cluster the data better. So the next step was to input features into existing machine learning algorithms, and I used the decision tree algorithm. My results show that 45% of the time, the tool predicted having difficulty when developers were actually making progress, and 31% of the time, the tool predicted making progress when developers were having difficulty. So these results are not good, and I know this when I compare them to the interaction approach. The interaction approach identifies more times when developers are making progress than the Connect approach. And this shows that the Connect results are much worse than the interaction results. The reason is because frustration is not equal to difficulty. And what I found was that some people don't change posture when in difficulty, so they tend to be calm, while other people change posture even when they're making progress. So these are the fidgety people. So the question was this a wasted effort? Well, alone, it didn't work well, but maybe if I combine it with the interaction approach, it would work better. This brings us to my next research question, which is, how do we combine the interaction and posture-based approaches? I use features from both approaches together. However, both features were computed at different time periods. For the interaction approach, it computed features every 50 commands, and posture computed feature every minute. So I decided to compute body posture features only when there was a programming activity feature. I used the same ratios in the previous iteration, except this time I split the edit ratio into insertion and deletion ratios. And I did this because I found that when people were having difficulty, they did a lot of deletion, which means their edit ratio increased, which is opposite of my previous results. This time my results were significantly better, surprisingly almost. 5% of the time, the tool predicted having difficulty when developers were actually making progress, and only 7% of the time, the tool predicted making progress when developers were actually having difficulty. How good are these results? Well, when I compare the combined approach to the interaction approach, the combined approach predicts progress more than the interaction approach. So it identifies more times when developers are having difficulty than the interaction approach. But it doesn't identify more times when they're making progress, but that's only slightly. And these results are statistically significant. They also provide evidence for my multimodal subthesis, which is, it is possible to develop an approach that combines programming activity and body posture recognition to predict when developers are having difficulty with their tasks, and has a lower false negative rate than existing approaches that only use programming activities to determine when developers are having difficulty. So I've shown the first part, I provided evidence to support the first part of my thesis, which is automatic difficulty detection is possible. Now, I'll provide evidence to show that it is useful, so I'll discuss my help awareness tool. What should a help awareness tool consist of? First, it should allow collaborators to become aware that developers are having difficulty. But before they can offer help, they need some context from the teammate. One form of context is screen awareness. Screen awareness is continuous knowledge of remote user screens. Collaborators continuously monitor developers' screens to see what is blocking teammates from completing their tasks. This idea is not new. T et al. Implemented it as a sidebar that allowed collaborators to monitor each other, and when they saw a potentially interesting event, they expanded their screens. A problem with this approach is that it may not provide enough information because it only shows current information, and previous work has showed that teammates need to know what developers have done so far to try and solve their problem. This can be modeled as a classic latecomer problem, which means it generally occurs in scheduled meetings when someone shows up late and they need to catch up. The most recent work on this topic was done by Sasha, one of Presuma's previous graduate students, and his colleagues at Microsoft Research. They developed a tool called AIR, or Accelerated Instant Replay, that allows latecomers to rewind the shared workspace, videos of participants' faces, audio, and it converts this audio to text or to transcripts. The goal of their work was to determine how much information one could recall. To do this, they compared the amount of information latecomers recall with different combinations of audio, video, workspace actions, and transcripts. Their results show that combinations of audio, video, workspace actions, and transcripts, and combinations of audio and workspace actions allow participants to recall more information than audio alone and any other combination. This suggests the combinations of audio, video, workspace actions, and transcripts are useful, but the results did not show that shared workspace alone, video alone, or text alone was useful. Therefore, their results do not apply to my latecomer scenario, because developers work alone until they get stuck, which means there's no audio, text, or video to replay. And the only information we have to replay is developer screens. Which brings me to my next research question, which is, how does replaying developer screens compare to non-replay? This comparison implies a lab study in which before developers must face difficulty, but this time observers must provide help. And there are many ways to do this. One is to use live developers and observers, where observers monitor developers' activities as they are performed. This was the approach used by Davish et al. And a game plan activity that was designed to support help giving. But there are several problems when you apply this approach to traditional software development. Since having difficulty is rare, this means observers must wait or perform some other activity until the next stuck point. One approach to overcome this issue is to allow subjects to monitor the activities of multiple developers, but this means they would have to be scheduled at the same time. Even more important, the study must involve multiple developers and subjects to reduce the impact of subject and observer idiosyncrasies, and ways must be made to allow observers to become familiar with developers' tasks and give them some kind of expertise so that then they can play a potential helper role. An alternative approach, the one I used, was to perform a two-phase study. In the first phase, studies play the role of developers, and in the second phase, they play the role of observers. I used screen recordings in the first phase. In the second phase, observers are shown screen recordings of other subjects, so they never see their own screen recording, but they see everyone else's. This should give observers expertise and allow them to become familiar with developers' problems. So to implement the first phase, I used screen recordings from a previous experiment. And in the second phase, 10 of the 14 previous participants were able to participate. Participants viewed screens under one of two conditions: replay, which means they could rewind and pause the screen, or non-replay, which means they could only view the screen, they could not rewind or pause. And I assigned conditions to tasks randomly. Another question was, what does it mean for observers to determine if they can offer help? A reliable solution is for them to develop a full working solution. But there are two problems with this. First, without the code base, it is not possible to develop a working solution. And second, this approach is overkill, because I assume that when observers find that developers are having difficulty, they communicate with them to help them get unstuck. To address these issues, I allow observers to outline the solution, and I use 2 raters to check if it was correct. Raters use a rubric to determine correctness, and I developed a tool that allow raters to determine whether the outline was correct or not. And if observers were correct, I assumed they were in a position to help. So now we have the study design. I need metrics to answer the research question I posed before. 2 metrics I created were correctness and time spent. And by correctness, I mean the average number of problems solved in the replay and non-replay conditions. And time spent is the time spent in replay and non-replay conditions. So first, let's look at correctness. On average, both coders showed that observers solved more problems in the replay condition. Time spent, however, observers spent 20% more time on each step point in the replay condition. The reason was that participants wanted to make sure they were given the right advice. And this is illustrated by the following quotes. One participant said during debriefing, "I used rewind to watch some portion of the video and to make sure it was correct." 2 participants made unsolicited comments. The first was, "When I couldn't pause or rewind, it was frustrating because sometimes I couldn't remember exactly what happened." The next participant said, "By rewinding, I could see what they did to get them into trouble in the first place." Even though participants took more time in the replay condition, they preferred replay to non-replay. And I determined this using a 7-point Likert scale, where 1 would strongly disagree and 7 would strongly agree. And I asked participants if they preferred to use rewind and pause than to not using it. And the average response was 5.63. These results provide evidence for my lab study of replay versus non-replay subthesis, which is replaying the programming action of developers who are stuck takes potential helpers longer to decide if they can offer help, but potential helpers prefer replaying programming actions to not having the ability to replay them. Encouraged by these results, I decided to test the tool in the field, which raises my next research question. Is it possible to build a help awareness tool that could be used for real work? Again, I tried this, and developers did not want to use an untested tool in their job. But during my stay here, I had to teach an object-oriented programming course, so I decided to take this opportunity to shape the help awareness tool. So this changes my research question to, is it possible to build a useful educational help awareness tool? And does field use uncover issues not raised by the lab study? The moment I tried installing screen awareness, I ran into the first issue. No student was willing to install it, and this was out of 35 students. But this was surprising to me because I thought students would like receiving the extra help. The reasons they gave was that they perform activities other than programming, and they did not want to share that information with me. In fact, one student emphatically said, "I don't want you looking at my Facebook page." Even when I told students that I would only record the Eclipse window, they were hesitant and would not install it. This experience forced me to step back and think of which ways that programming context can be shared and ways that will be acceptable to my students. Programming context can be shared at multiple levels of abstraction: the frame buffer layer, the window layer, the toolkit layer, or the data layer. And the amount of information shared decreases as we move up layers. My screen sharing tool was at the frame buffer layer. So to provide the least amount of information, the data layer should be shared. But what data should we share? Since we're talking about programming, we can share methods, the status of programmers such as editing or viewing a file, or their code. previous work has argued that a collaborative IDE could allow developers to determine if they should offer help. So this is the approach that I used, and I built a tool named Eclipse Helper, which has two views. It has a student view, which is buttons that allow students to correct the incorrect status or manually indicate their status, and an instructor view, which I use, which notifies me when students are having difficulty. And it has status buttons that change from green to red when they're having difficulty, and back to green when they're making progress. And a view project button that, when pressed, shows students' edits in my programming environment. This time, I had much more success with students installing the tool. In fact, 30 out of 35 students installed Eclipse Helper. As I mentioned before, there are two ways to get help. You can either ask for help, or someone could observe it through automatic detection. So far I've assumed that automatic detection is actually better, but I wanted to see if it truly was. So what I decided to do was require students to manually indicate their status. And what I found was that only one student pressed the slow progress button to indicate a need for help. This was surprising because some students did not perform well on the assignment. So when I asked why, they said they don't want to bother me, they were not sure if I was available to help, and when they were having difficulty, they didn't remember to press a button because they wanted to solve their problem. These responses are consistent with previous work, which shows programmers are late or hesitant to ask for help. And in this case, the students were late or hesitant because of inhibitions, lack of health expectation, or being overwhelmed. How do we address this problem? Well, I announced my availability and willingness to help. And this brought an even bigger problem. Students asked me for help for everything. So to address this issue, I stopped announcing when I would be available to help, and I turned on automatic difficulty detection in the tool. And this was with the interaction approach. I didn't use the connect here. I still had one more concern. Would students be unnerved with help seeming to come from nowhere at unanticipated times? Students who were helped said it was not a problem because they knew it was possible to receive help when they were having difficulty. So how was help offered? There are many ways to communicate, such as audio or video, and textual means. And with text, we can communicate with email or instant messaging. And I chose to use email because it was the simplest form of communication. I entered into an email discussion with the students, and help was given with references to background material or a description of how specific errors could be fixed. So how did this process work? Well, let's look at specific difficulties students had and how I helped them. So I sent an email to a student asking him if he needed help after watching him trying to fix compiler errors for a few minutes. And the student replied, "Yes, I'm having a few problems. I'm getting an error message and it won't recognize that I'm using methods from the A-vehicle class." So I replied to the student, "Review how to write a method that takes parameters and how to call a method with parameters." A few minutes later, the student replied back, "Thanks, that fixed my problem. I struggled with that for over an hour." This help episode shows the students were appreciative of the help that I offered. They were also appreciative of my willingness to help and a tool that allowed just help to be offered. And this is demonstrated by the following response to a help inquiry. The student said, "Cool to see that the help is working. Thanks for asking me what is wrong." So I've shown you two positive experiences, but there was also a negative experience where a student could not overcome his difficulties. So a student was having trouble with conditionals, so I sent them an email saying, "Are you having issues with your if statements in your while loop, and the while loop as well?" And the student responded back, "I'm having issues with my while loop and if statements. I'm not sure exactly what I'm doing wrong. It only lets me enter commands once, and after that, it doesn't print anything." After several email exchanges, the student did not solve his problem. The reason was that the student had difficulty explaining his problem, and he would prefer to point to the screen to explain his problem than try to explain it through email. So this made me wonder, since this student wanted to use screen sharing, would the other students want to use it? So to answer that question, I surveyed students before the last assignment of the semester, and this time, half of the students in the class were now willing to use screen sharing too. The reason is that they trusted me more now than at the beginning of the semester. And they said it was easier to point to something on the screen than explain their problem through email. During this 2-week study, help was given to nine times to 8 students. These results provide evidence to support my field study of a help awareness tool sub-thesis, which is, it is possible to build a difficulty detection tool that is successfully used to offer help to students. So I've provided evidence to support my thesis, which is automatic difficulty detection is possible and useful. And I composed this thesis into 6 sub-theses, 4 of which I presented here. So I presented these 3 and the top one. I did not talk about these 2, which is difficulty level and barrier detection. It is possible to develop an approach that uses developers' interactions with their programming environment that A, automatically determines the barrier that is blocking programmers from making progress, and B, automatically determines the level of difficulty programmers are having with their tasks, and C, it performs better than baseline measures. And my reusable difficulty detection framework, which is, it is possible to develop a common set of difficulty detection modules for different programming environments that have significantly fewer lines of code than difficulty detection modules written specifically for each programming environment. There are several limitations on my work that can be addressed by future work. So in all of my studies, developers implemented programs from scratch. Maintenance tasks can be expected to have more navigation for the same difficulty degree. So it would be useful to create a single mechanism for detecting difficulty in both the development of new software and the maintenance of existing software. It would also be useful to increase the performance of the difficulty detection mechanism. So we could perform more iterations to investigate additional features, such as idle time, facial expressions, sweat, or the amount of pressure put on the mouse. I can also investigate different log segmentation methods, such as using dynamic sized segments that are overlapping and segmented by the amount of time. And one could explore this whole design space. I've shown that help awareness is an application of difficulty detection, but there are other applications, such as estimating an individual's or a teammate's progress, clustering problems according to their difficulties, and informing developers in difficulty about the actions of others who overcame similar difficulties so that they may take similar actions. It would also be useful to determine whether my results apply to a broader range of software engineering courses, industrial training and mentoring, and teams of programmers in educational and industry settings. So I would like to thank my advisor, Prasoon Nuwan, members of my committee, Chris Wisen from the Odom Institute, who helped me with my statistics, my Cisco family that's here, specifically my manager George. I was supported by the NSF, my wife and my mom, user study participants, my colleagues and friends.